Hi, this is Emma, and I'll be telling you about a new connection between depth from defocus and the transportive intensity equation. So the depth from defocus problem in photography seeks to recover the depth of a scene from images captured under different focus settings. Similarly, phase retrieval in microscopy determines object phase by comparing intensity captures at different planes. Both of these problems have been considered in a differential setting with depth from differential defocus in photography and the transportive intensity equation, or TIE, in microscopy. We show that by connecting these two equations, depth from defocus can be seen as a special case of phase retrieval. As a quick review, phase refers to how far along a wave we are, like if we're sitting at a peak or a trough. So if this plane wave illumination encounters a thin refractive object, it will be delayed the least where the object is thin, getting a head start there. And so the thickness and refractive index of the material are transferred to the phase delay in the outgoing wave. We call this delay the object's phase, and that's what's recovered in phase retrieval. Because of its relationship to the thickness of the sample, it can be thought of as an analogous quantity to depth. But we're going to show that this is not the right way to relate phase and depth if you want to connect phase retrieval and depth from defocus. So to model this relationship properly, we're going to take a step back and start with a look at the qualitative differences between defocus in cameras and in microscopes. So here's a typical image from a camera shown with this flower in focus. And when the image is defocused by moving the camera away, we can see that the flower is going to get smaller and blurrier, and we lose high frequency features like those stripes on the petals. So in contrast, this is a typical image for coherent phase microscopy. So the three cheek cells that are shown here cause very little variation in brightness because they're largely transparent and they're imaged in focus. But I'll show you a sweep through the focal stack. And in the defocus regions, both in front of and behind the cells, the images look quite different. So here we are before focus, in focus, after focus, and one more time, out of focus. So when we talk about defocus in photography and microscopy, both the image content and what happens to it are very different. And we can start to break that down by looking at the kinds of objects that each system typically observes. So in photography, we often assume that the world is made up of Lambertian planes, which are opaque surfaces that reflect light isotropically across angles. In phase microscopy, we observe phase objects, which are largely transparent and deflect the light that is shown through them. Now, we could take this flower picture with a microscope or this cell picture with a camera, but they'd be violating common assumptions in each setting. So for example, someone from a microscopy background might think of the photographic scene as a dense collection of point sources or an amplitude mask that's illuminated by an incoherent source. Likewise, photographers can think of phase images as photos of glass objects or fluid surfaces. Now, the difference in the effective defocus comes down to the coherence of the illumination. Photographic scenes are almost always incoherent, and this leads to a loss of high frequencies in the image under defocus. But coherent defocus can actually create new high frequency features in the intensity, not in the field, but in the image intensity. So the difference here is that in the incoherent case, we can think of defocus as a convolution with a low pass filter on the image, but coherent defocus is a convolution that changes the phase of the complex electric field. And so the nonlinearity going from field to intensity means that this process is not linear in the image intensity domain. Okay, so let's break down these differences between cameras and microscopes, with the caveat that these are generalizations. So you could find exceptions to everything I'll say here, but these are very typical assumptions for the two problems. So for our simple camera, consider a single lens imaging system. And for the microscope, we'll assume a 4F system with just ideal thin lenses in each. So right away, we see that the camera has a perspective projection, so the apparent size of an object will change with its depth. But the microscope is telecentric, and this won't happen. We'll also assume that the camera looks at incoherent scenes where there's light propagating in all directions, while the microscope's illumination will be spatially coherent with only one direction. So that explains the differences we saw in the effects of defocus on both image size and frequency content. What we haven't done yet is connect that to the depth or the phase of the objects they observe. And we'll do that by taking a defocus change. So there are many ways to defocus an image, but we'll say that there's a specific depth where objects are imaged in focus, and we'll take a step away from that depth to generate the defocus. And in fact, we'll be looking at a differential step in depth. So to understand what happens when we do that, we'll use a mathematical object called the Wigner Distribution Function. There are a lot of good sources out there that walk through all the details, both from the optics perspective and the computer vision perspective. But to first order, you can think of this as essentially a light field that captures wave optics phenomena. So for a plane wave passing through an aperture, the light field would have supported a single angle across the width of the aperture. But the WDF would include diffraction at the edges in that vertical spread in red, and it would also contain destructive interference, which is modeled by the negative values shown here in blue. And this object lets us talk about phase in a more general way. So let's say we have a locally linear phase object. That's going to be a section of a prism. And when a single plane wave passes through this prism, it will be deflected, as we saw before. And so a phase ramp, d phi dx, corresponds to a deflection in the direction u. And we can reverse that, actually, to take this as a definition of the phase from the propagation direction. So that works great for coherent illumination. But under partially coherent illumination, multiple plane waves will encounter this object from different directions, and each of them will be deflected independently. So now we don't have a single well-defined phase or direction at each point in space. So this previous relationship doesn't make sense anymore. But we can consider a generalized phase, which is defined again by its spatial derivative as before, but now it's going to be related to essentially the average direction of propagation. So this is going to be a sum of all of the directions u weighted by the radiance-like values of the Wigner distribution function. Okay, so now we have all of our pieces together. We understand how and why these defocused images are different, and we've got some good mathematical tools. So now we can connect them for a direct relationship. And to do that, we'll have them meet in the middle with partially coherent illumination, telecentric optics, and a differential step in defocus. So what happens under this defocus change? We have two answers. They're going to look a little different at first. So our slightly modified depth from defocus answer is that the change in image intensity due to a differential defocus step is going to be proportional to the scene depth and the image Laplacian. But this is going to come with some assumptions. So first we take the paraxial approximation, but we'll also require a Gaussian apodizer or aperture code. And additionally, we'll require an object with a well-defined depth, like a Lambertian plane or a point source that has some angular isotropy at that depth. And this is leaning pretty heavily on the assumption of partial coherence, right? So this is going to break down as the scene becomes more coherent. And on the right, we have a more general answer from the transportive intensity equation, which says that that image change from the defocus step, now with this additional wavelength term, can be related to derivatives in the image I, that's the intensity, and the phase phi. And it turns out that this actually applies to the generalized phase I showed you as well, okay? And all that's needed to derive this is the paraxial approximation. So we can see right away that this is a very general equation on the right, and the depth from defocus equation adds assumptions, which makes it a special case. So let's dig into that, right? What are these assumptions doing to reduce TIE to depth from defocus? So the first assumption was that a defocus point gets imaged as a Gaussian. So paraxially, we can approximate a point source as a quadratic phase profile, and then we just require that the image should be a Gaussian. So we can see this matching quadratic term and say that in this instance, where we have a single point source in our WDF, the phase is in proportion to the log brightness, and this is using the classic definition of phase. Now that looks kind of coincidental, but it turns out that this generalizes to these depthy objects, right? Objects with an angular isotropy at some distance z, such as Lambertian surfaces and ensembles of mutually incoherent points. So essentially any WDF that has this structure, right, where there's a locally constant slant in the WDF content, and there's this Gaussian weighting across the directions. So if those two conditions hold, the generalized phase defined by the WDF will be linear both in depth and log brightness. And this condition is going to allow us directly to reduce the general TIE to the special case of depth from defocus. So what does that look like? We take the TIE on generalized phase, and we plug in our constraint on that phase. And it just reduces immediately to the modified depth from defocus equation. It's just plug and chug at this point. And this is exciting because these are both useful equations. The one on the right gives you phase derivatives that you can integrate to get the object's phase. And the one on the left says that you can get the depth of an object just by comparing this defocus derivative and the spatial derivative. But that's not the only depth reconstruction method that the theory suggests. Another way is to observe that the phase constraint, when rearranged, shows us that we can convert a generalized phase measurement into a depth measurement just by dividing out the log brightness and accounting for a calibrated constant. Now, computationally, this is going to be slower and less stable than the direct method, but it demonstrates the deep connection between these quantities. So let's look at what happens in a toy scenario. I'll take a phase and amplitude object where the phase has these three little bumps and the amplitude has these chirp stripes. And we'll simulate what that looks like, slightly off focus. through a Gaussian apodized 4F system under high, medium, and low spatial coherence illumination. So here on the left, I'm representing the angular extent of each illumination source, and it becomes wider as we lose spatial coherence. Now, in the high coherence case, the phase of the object shows up as a jagged line in the angular support of the WDF. And the generalized phase in blue matches well with the object's true phase in dotted black. But both depth methods will fail in this case. We don't recover the true value shown in dotted black, which is a constant out of focus depth. Now, in the low coherence case, the illumination fills the aperture. And so the angular support of the WDF is no longer informative as to phase. And instead, those slanted stripes encode depth by the extent of their slant. So in this case, the generalized phase in blue is very different from the object phase in black, but depth can be recovered well. So this matches our expectations. The phase results are good in the coherent setting, and depth results are good in the incoherent setting. Where things start to get maybe a little more interesting is the medium coherent setting. So in this case, between the extremes, both the zigzag shape indicating object phase and the slanted stripes encoding depth are partially visible. And in this regime, phase and depth are both degraded significantly, but very rough estimates can still be recovered. So in partially coherent settings, or settings like fluorescent phase microscopy, where coherence varies spatially across the image, both methods may have something to offer, particularly for high-speed applications where capture and computation time are extremely limited. These differential methods allow very fast measurement of both phase and, where applicable, depth. So what we've learned is, rather than just interpreting phase as an analog to depth, there's this generalized phase quantity that's recovered by the transport of intensity equation. And when the scene content is spatially coherent, this generalized phase is identical to the standard definition of phase, but when all or part of the image scene is incoherent, we can reinterpret the generalized phase as a depth measurement by correcting for image brightness. This shows that depth from defocus in photography can be seen as a special case of phase retrieval methods in microscopy. So thank you for listening, and thanks also to my collaborators.